Welcome. This is the fourth video in our study of Eratosthenes' sieve as a discrete dynamic system. In this video, we will now develop the relative population models across the various gaps in the cycle of gaps for Eratosthenes' sieve. Where we've seen to this point, we have a general model for the exact population of gaps. So if we take our initial conditions from the cycle of gaps for the prime p sub 0, then for all gaps up to 2 times the next prime, 2 times p1, we're able to develop the exact population model, and that's this linear system. It's a j by j system where the length of the longest driving term for that gap is capital J. We've already seen that we can get a nice concise eigenstructure expression for this system. With spectrum, the dominant eigenvalue is the product of the prime minus 2 as the prime q runs from p1 to pk. And then the other eigenvalues have a similar form of prime minus j minus 1. We've seen that all of those are super exponential and become unmanageable very, very quickly. So what we do is we factor out the super exponential growth. Let's isolate the super exponential growth and look at the coefficient, the exact relative population of gaps. So when we divide away that super exponential growth, we get this linear system. It's the same banded matrix with on the main diagonal, we now have a 1 in the upper left corner, then prime minus 3 over prime minus 2, all the way down to that lower right corner. On the super diagonal, we have that 1, 2, 3 up to capital J minus 1, all divided by prime minus 2. So taking the same approach to the analysis, we apply this iterative system, unpack it all the way down to the initial conditions, that starting point of p sub 0 primordial. It has the same similar eigenstructure. The right and left eigenvalues are the same. The matrices of eigenvalues, those lambdas, are all diagonal, so they collapse. And our spectrum now, the dominant eigenvalue is 1. So these models converge as primes go to infinity and the parameter lambda goes to 0. And for lambda, we use that subdominant eigenvalue. So that lambda sub 2, that's what we will later call lambda. This is prime minus 3 divided by prime minus 2 as q runs from p1 through pk. And you can see the expression for the other eigenvalues there. These models are all big O of 1. Their asymptotic values are all proportionate across the various gaps. This is a graph of those relative populations. This is the graph of the W's. So these are the relative populations of the gaps in the cycle of gaps. And in this picture, we've started over there on the right-hand side with p sub 0 is 37. We set the parameter lambda at 1. Lambda is that subdominant eigenvalue of prime minus 3 over prime minus 2. So then we let as the primes go to infinity, lambda goes slowly to 0. We can see if we look at the right-hand side there, we have 6 up top. It'll go over time to about twice the population of the 2s and 4s. The 2s and 4s are a good reference point. They're the constant weight of 1. We see 12, the dotted blue line, it's starting below 8s and 10s in 37, in the cycle for 37. It quickly passes up 8 and then 10. At about 0.5, it'll pass up the 2s and 4s, on its way also to being about twice the number of 2s and 4s. And we see that 8, even though 8 has driving terms of length 3, it never passes up the numbers of 2s and 4s. It grows over time slowly, but its asymptotic value there over on the left is also 1. So here, since we're working with the initial prime 37, that bound from observation 1, we can work up to twice the next prime. So we can get models for all the gaps up to 2 times 41, or 82. So all the gaps up to 82. And here's a picture then of all those models. Each of these models has the form of an alternating sum. This is if we go and extract the top row from the eigenstructure, from that eigenstructure matrix. The model for the gap itself is its asymptotic value minus a coefficient L sub 2 times that subdominant eigenvalue, the prime minus 3 over prime minus 2, plus a coefficient times the next eigenvalue, and so on. The coefficients, L sub j, is the corresponding left eigenvector times the vector of initial conditions. Same as the left eigenvector times the raw population of initial conditions, dividing out the super-exponential growth to that point. And we have to do that. We have to keep the models up to length j of the longest driving term for the gap g. We get a Polignac result. So in the cycle of gaps, every even gap does indeed arise. Pick any even number. That even number will arise as a gap in the cycle of gaps. And even though that gap it lies beyond, maybe even well beyond, that bound of 2 times next prime, 2 times p1, so we cannot develop its full model, but we are able to calculate its asymptotic value. We can get that first number in the model. The asymptotic value for any gap G is a product of Q minus 1 divided by Q minus 2 as Q runs over all the odd primes dividing the gap. And this is exactly the coefficient that Hardy and Littlewood anticipated. They estimated this and conjectured that these would be the ratios. They are indeed the ratios, or become the ratios, in the cycles of gaps. Here we're showing the families to illustrate this. Here we have, in this graph, we have removed the multiples of 7s and 11s and 13s. Here we have the gaps up through 82, all of whose factors are either 2, 3, or 5. So the powers of 2 is that red family at the bottom, and they all converge to 1. If the gap has factors of 2 and 3, we've labeled that family 6, and that's the blue family there, 6, 12, 18, 24. But when we get to 30, that family has factors 2, 3, and 5. So they're in the orange and the gold up top. We have 30 and 60. If the family just has the factor of 2s and 5s, that's the green family, 10, 20, 40, 50, 80. We've color-coded the families of gaps by their asymptotic value. The power of these models. With the models, we are able to calculate the relative populations of gaps in the cycles of gaps far beyond what we could calculate directly. By way of example, the cycle of gaps for the prime 199 has more gaps than there are atoms in the known universe. So we cannot directly calculate the cycle of gaps anywhere near that far. The interesting parts of the models here, as gaps grow and sort out sort of into their asymptotic order, these take place over incredibly large primes. We don't cross below 0.25 until primes around 3 million. And we don't cross below that system parameter lambda equal 0.15 until we're working with 11-digit primes, 6 times 10 to the 10th. Zooming in on the left-hand side of these models, let's take a look at what happens down below 0.1 for that system parameter. And this also gives us a sense of how slowly lambda converges towards 0 as primes grow. We can see that we cross below 0.1 around 17-digit primes, 1 times 10 to the 16th. We see that 30, that orange gold line up top, finally becomes more populous than 6s. There are finally more 30s than 6s in a cycle of gaps when the prime is around 2 times 10 to the 19th, around when the system parameter is around 0.083. We would have to go that far out. Anything we study before that, 30 is not represented the way it will be eventually. And then that system parameter doesn't get down to 0.05 until 2 times 10 to the 32 for the prime. And the system parameter lambda does not get down to 0.01 until we are working with 163-digit primes. So we're able to model the gaps up through 82 and develop complete models for their relative population in the cycles of gaps across stages of Eratosthenes sieve. What about larger gaps? What about gaps that are beyond the reach of our current models? Well, we're able to calculate the percentage of total gaps represented by the gaps up to 82. That percentage is depicted here in the red curve. We show that through the first 100 million primes, in fact, through the first 10 to the 12th primes, 99% of the gaps are at most 82. In fact, over the computational range, shown here in the orange at the left, up through that computational horizon, the gaps up through 82 still represent 80% of the gaps in the Eratosthenes sieve, in the cycle of gaps at that point. For the computational horizon, we first use 1.5 times 10 to the 23rd. That's the total computer storage on the planet Earth right now. So that is one mark for the computational horizon. And past that, we mark 0.1 for the system parameter. Be very ambitious for us to reach that horizon in any sort of exhaustive way. Models provide strong evidence for Polignac's conjecture. All even gaps do arise in the cycle of gaps. The twin prime conjecture, the 2s are among those, and Hardy and Littlewood's estimate of the products of prime minus 1 over prime minus 2, that asymptotic estimate about the relative frequency of various gaps. These are all true in the cycle of gaps. The only dependence on the gap itself is in the initial conditions. The dynamics only depend on the prime and not on the gap. All of the gaps are subject to the same dynamic system. We don't see any preference for or against any particular gap. So this is the path ahead. We have a pretty thorough study of the gaps in the cycles of gaps for the stages of Eratosthenes sieves. We want to connect these to gaps between prime numbers. So we'll look at surviving the sieve. We'll look at the front of the cycle, 0 The first fusion will take place at the next prime squared. That's the first composite number after we've run Eratosthenes sieve up to a prime. It's the next prime squared is the first remaining composite number. So we'll look at the interval of survival from this prime squared to next prime squared, and we'll take data samples in those intervals of survival and compare them to the models we have. And let's see how well these models are predicting what we should see amongst prime numbers.